So far, we have considered the reaction of free radicals with the sigma bond of the alkane. And we said that there are two types of free radicals, a bromine free radical and a chlorine free radical that we can generate. Bromine free radicals, these are very selective, and those are going to produce one product only. They are going to replace the weakest bond, which is the most substituted hydrogen. On the other hand, the chlorine radical, these are going to be very reactive, and you're going to end up getting multiple products. In this section, we are still in the reaction of free radicals with the sigma bond. But instead of the free radical replacing the alkane hydrogen, the free radical is going to come and replace the allylic hydrogen. They can also take the benzylic hydrogen. We've talked about allylic hydrogens and benzylic hydrogens, and we said that these are the weakest sigma bonds. So free radicals can easily take these hydrogens. Now, the free radical that we are going to consider the reactions of allylic and benzylic hydrogen with is going to be the bromine free radical, not the chlorine free radical, since the bromine free radical is more selective than the chlorine free radical. If there is any allylic or benzylic hydrogen, then the free radical bromine is going to favor this hydrogen over the tertiary hydrogen. There are two ways of making a bromine free radical. The first way we already talked about. So to make a bromine free radical, simply start with a bromine, react that with light, and you get bromine free radicals in there in the initiation step that starts the reaction. This is the first way. The second method is to use MBS. Now, MBS is N-bromosuccinimide. It has this Lewis structure. The nitrogen is connected to the bromine by a sigma bond. We abbreviate this as NBS. This is how you're going to say it, but you are responsible to know its Lewis structure. And this is called N-bromosuccinamide. Now, it's N because the nitrogen is connected to the bromine, so this is why we call it an N-bromo, and this is the succinimide part. We said that the sigma bond that connects two electronegative element is normally a weak sigma bond. So whenever you react MBS with light, what's going to happen is that a homolytic cleavage in there, as we used to, and each atom will take an electron. So you will end up getting the succinimide radical plus the bromine radical. Bromine radical is more reactive, and this is going to start the reaction. Whenever you have MBS in presence of light or bromine in presence of light, and you have an allylic hydrogen, something like this, let's consider an easy example first. So you have, this is an allylic system, and here you have one type of allylic hydrogen, just one type of allylic hydrogen. Then if you use MBS in presence of light, these two are going to react together and you're going to generate a bromine free radical. I'll consider the mechanism as we move on. That the bromine free radical is going to replace the allylic hydrogen. It's a simple substitution reaction. Of course, this is not SN1, this is not SN2. It goes by a homolytic cleavage in there. It's a free radical reaction where hydrogen gets substituted by the bromine. Notice that the reaction is on the allylic carbon replacing the allylic hydrogen. The reaction here is never on the double bond. Let's go ahead and consider the mechanism of the reaction. Now, in these reactions, you are going to get more than one product. And the products, the number of products are going to depend on how many allylic hydrogens you have and how many different allylic radicals that you are going to create by resonance throughout the process in the mechanism. This is why the mechanism is very important for those. So this is how the reaction is going to look like. So the question here is going to be find all the products. Okay. Now, the moment you see light, then you know that this is a free radical reaction. It goes by a homolytic cleavage. And homolytic cleavage means three steps: initiation, propagation, and termination. Let's start with the initiation. So the first step in there. So this is the initiation. And in the initiation, you have your N-bromosuccinimide, and you're going to react this with light. Light is going to target the bond that connects the two electronegative elements, and you are going to cleave that bond by a homolytic cleavage, and each one of these electronegative elements is going to take an electron. So you're going to end up having a free radical on the nitrogen and a free radical on the bromine. Okay, now the bromine here is very reactive. So this guy here is going to be very reactive. This is what I'm going to take it, and I'm going to proceed my reaction with that. But remember what we did whenever we were doing bromine in presence of light. We said that not all the starting material is going to cleave by light. Some of the MBS is going to remain unreacted. So I'm just going to go ahead and write here plus unreacted MBS. Okay, so that's going to be the first step in there. The second step. So in the second step, this is the propagation, and we said that in the propagation, this is the steps where you get your product, and it is two steps. Step one, you start with your reactant, and you react this with the free radical. Bromine free radicals, they are selective, and because they are selective, they're going to choose the most stable hydrogen and replace it. Here in this case, the most stable hydrogen is the allylic hydrogen, because here you do have allylic carbons. These are our allylic carbons. Always start numbering from the double bond, and the carbon which is on carbon number 3 of the double bond, that is going to be an allylic carbon. Notice that these two carbons are the same. So I'm just going to go ahead and consider just one of them. Okay, so I'm going to consider the allylic hydrogen over here. This is going to be my allylic hydrogen. And the bromine radical is going to immediately come. Remember, radicals, they take hydrogens. So it's going to immediately come and take this allylic hydrogen, and it's going to make an allylic radical. So it's going to make an allylic radical. This is a half head arrow. So let's represent it as such. And you're going to end up getting your allylic radical in this case. I'm going to go ahead and write it over here since I need some room. So here you go. So you're going to make an allylic radical. Now, this allylic radical that you're going to make is a secondary allylic. Every time you make an allylic radical, you have to do resonance if possible. And always you have to do resonance, because it's always possible to do resonance in there. So the resonance is a must, because whenever you do resonance, you're going to generate a different free radical. So you're going to end up getting a different product. Remember what we said about free radicals, allylic and benzylic, they all form. So whether they are primary, secondary, or tertiary, they are all going to form. So let's go ahead and do resonance with these allylic free radicals in there. So start with the electron and move the electron towards this carbon. So now you can easily see that I'm creating another radical. And that other radical is the primary radical in this case. So that is going to be the primary allylic. Okay, so you see the difference in there. Now I'm going to take each one of these radicals now, and I'm going to react it with the second step of the propagation. So it's always a must. Whenever you're doing the first step of the propagation and get your radical, go ahead and react it, or go ahead and do resonance so that you can get another form of the allylic radical. Now in the second step of the propagation, now here's the thing, before I start with the second step of the propagation. So I said over here that you will have unreacted MBS. that unreacted MBS is going to immediately come and react now in the second step of the propagation. But the MBS is not going to react with the radical because it's going to be unreactive with the radical. The MBS is going to react with the HBr that is formed whenever the bromine radical takes the hydrogen. So over here, I'm going to end up getting an HBr. So the moment you form an HBr, then we're going to have that side reaction that is happening with the unreacted MBS. So the unreacted MBS is going to come. MBS is very reactive towards hydrogens. So here you go. And that is going to react with HBr. When it reacts with HBr, the nitrogen is going to come and take a hydrogen. So you're going to end up getting a hydrogen next to the nitrogen in there. That is going to be the succinimide plus the bromine, the Br2. So it's that Br2 that is going to react in the second propagation step. So now in the second propagation step, I'm going to consider each free radical alone. And I'm going to react it with the bromine. And this bromine is formed whenever the unreacted MBS, so this one is the unreacted MBS from the first step of the initiation, reacts with the HBr that is formed from the first step of the propagation. They make a bromine. So now that bromine is going to come and react with each one of the allylic hydrogens. So now with the second step of the propagation, I'm going to take each free radical alone. So I'm going to take my first free radical and I'm going to react that with the bromine to get the product, the first product. And here always you have to consider stereochemistry. Remember, if you are generating a chiral center, please consider stereochemistry. So here I am generating a chiral center. So free radical in there is going to come, it's going to react with the bromine. And then I'm going to generate a bromine free radical in there. The attack can be either from the top or it can be from the bottom. So I'm going to end up having two stereoisomers in this case. Write all your stereoisomers, please. So I'm going to end up having my replacement of the allylic hydrogen with the bromine, and the bromine can either be on top or the bromine can be at the back, since I am generating a chiral center in this case. So these are the first two products for the secondary allylic. Now let's do the primary allylic. We're still in the second step of the propagation. So with the primary allylic now, we're going to do exactly the same thing. Now, the primary allylic is going to form similar to the secondary allylic. Now, the secondary is going to be more stable, but both are going to form and both are going to react with the bromine in the second step to form the product. So you have to list all the products in there. There is no preference of a major product with these allylic systems. So plus a bromine over here. Here I'm not generating a chiral center, so I don't need to bother. Here you go. So I'm going to end up getting just one product in this case, which is the bromine. So notice that in this reaction, I got the three products. Plus, of course, the bromine radical. So this reaction is going to keep going on because notice here that you have another allylic hydrogen. You have an allylic hydrogen over here. You do have also an allylic hydrogen over here, and you have an allylic hydrogen over here. So the reaction is going to keep going on, and you're going to replace those allylic hydrogens unless you stop the reaction. So this is why it's very important with these types of reactions to stop them immediately whenever you get your desired product. So here C, let's do termination. Termination is going to be a lot of radicals, because during this process, notice how many radicals you are forming. You are forming the bromine radical, you are forming the succinimide radical. So a lot of radicals in there. So we're going to limit our termination again to only 3 steps. So only choose 3 radicals and react them with each other. Um, the reaction normally where you react radicals together. So when radicals form bonds, this is called a coupling reaction. So when you have a radical forming a sigma bond with another radical in here, this is called a coupling reaction. And you're going to terminate your radicals in there. The ones that start the reaction are the bromine radicals, so it's very important to terminate this. Start with that. We can also terminate let's say, this is going to be one, okay? And then let's do this one over here. Let's go ahead and first, let's do the MBS. So we already created this radical here. We can react it with the bromine radical that is forming and make the MBS. Okay, so that we can also stop the reaction. And then the third free radical that you want to choose is any of the hydrocarbon free radicals that you generated. So let's go ahead and choose this one. You can choose any. You don't have to write them all. Here you go. You're going to react this with another one of itself. And this is going to be a coupling reaction in there. And you are going to form a bond between those two cycles. Of course, you have different possibilities in here because you can react this radical, so you can react those two radicals together. You can react this one with itself, this one with itself. So a lot of possibilities in there, but we're going to limit the termination steps to 3 termination steps. Let's consider another example. In these reactions, as I said, the product is going to be more than one product, and it depends on the allylic radical and the resonances, the different resonances that form from the allylic radical. So here again, the reaction is going to be with MBS in presence of light. It can also go with the bromine in presence of light, so the same mechanism in there, and the bromine will take the allylic hydrogen. So let's go ahead and count how many allylic hydrogens we have. So I have an allylic hydrogen here, and I have an allylic hydrogen over here. Okay? So let's start and take the first allylic hydrogen. I am numbering them. So I'm gonna skip initiation because you know initiation. Now I'm just gonna go ahead and write the propagation steps. Okay? So let's do the propagation step for allylic hydrogen 1. And this is how I want you to write the mechanism of the reaction when I ask you to write the mechanism of the reaction. So let's go with the first step of the reaction. So step A, and there you start with your allylic system. That is the allylic hydrogen over here. And you're going to react this with the bromine radical that you made from the MBS. So the bromine radical is going to come. It's going to take the hydrogen, and you're going to generate an allylic radical. Now, this allylic radical is going, of course, to undergo resonance. So you have over here an allylic radical, and there. So the allylic radical is going to undergo resonance. So go ahead and draw all the resonance structures for this allylic system. And always start with the free electron. So you have an electron coming here, another electron going there, and you're going to generate a free radical on this carbon, a double bond in there. This is going to be a primary allylic. This is going to be a tertiary allylic. Both form. Tertiary allylic is slightly more stable, but both are going to form. So now once you get your allylic free radical, we're going to react each one of those with the second step of the propagation. And in the second step, the MBS is going to react with the HBr as we set up. And you're going to make bromine. the bromine is going to come and react in the second step. Now, when the bromine is going to react, the free radical is going to be abstracted by the bromine, and you're going to generate a bromine free radical. Since you have a potential chiral center, so look here, you do have a potential chiral center, so the attack of the bromine is going to be from the top or from the bottom. Please consider all the stereochemistry in there. So if it is going to be from the back, then the CH3 is going to be in front. And of course, I have a CH3 over here, plus the bromine radical, plus if the attack is going to be from the top, then the CH3 is going to be at the back, plus the CH3 over there. So these are the first two products when you have a tertiary allylic system. Now let's do the second propagation step for the second type of the allylic, which is the primary allylic. So now I'm going to have my bromine. This is the second step of the propagation. Write the lone pairs. Here I didn't show the lone pairs. Please show the lone pairs of the halogen. So I'm going to start my reaction in there. The free radical is a little bit far away, but here you go. Make sure that you start your arrow from the sigma bond towards the bromine. So now I am going to form my primary allylic, but now the primary allylic is not a potential chiral center, so you don't have to consider the stereochemistry of the reaction. This is the carbon, the allylic carbon over here, and that allylic carbon, I didn't do anything to it. All I did is simply I added a bromine in there. And then you're going to end up having the rest of your substituents on the cycle. So the first allylic hydrogen here generated 3 products. Let's go ahead and do the second allylic hydrogen. So this is going to be step B. Please label your steps in there. So that is going to be step B of the propagation. So you have step A of the propagation and then step B of the propagation. We are going to continue for the allylic hydrogen 2. So for allylic hydrogen 2, then we're going to do exactly the same thing now. We are working with this allylic hydrogen. So we're going to do the first step of the propagation. So that is going to be my allylic hydrogen. And I'm going to react this with the bromine radical from the MBS. So the radical always takes a hydrogen, and you're going to generate a radical on the allylic carbon. Then you're going to do your resonance. Okay, so here you go. And then you're going to go ahead and do the resonance. Now, doing the resonance, you're going to generate a primary free radical. Now, the second free radical that I am generating here is different than the one that I generated up. This is going to be my primary, but now my double bond is on this side. See the difference? The double bond is here, the double bond is there. So there is a difference. If you generate radicals that are the same, then neglect whatever duplicate you are generating. But make sure to point out the radicals that are different, because they're going to get you different products. So here I'm going to end up having the secondary allylic versus the primary allylic, and we're going to do exactly the same thing in the second step of the propagation. So for the second step of the propagation in there, this is going to be step B. Label your steps, please. Now the bromine is going to come and attack. Mind the stereochemistry as we did before. You will be forming a chiral center in here for the first allylic hydrogen. So the bromine is going to come and it's going to couple with the free radical. And then you're going to end up having a free radical on this bromine. That is going to be my first allylic substitution. It is going to be a chiral center, so the bromine is going to attack either from the top or from the back. And here in this case, I will be making diastereoisomers. These are chiral centers that I didn't touch. They are still the same in there. So I will be making a chiral center in this case. So the bromine is going to be at the back. Don't forget your substituents. Please put your substituents in there. So these are my two products for the first allylic hydrogen. For the second allylic hydrogen, the second step in there, let's write the bromine up so that we are close when we do the mechanism. Okay, so over here, the bromine is gonna come, the bond, okay, is gonna come and couple with this free radical, and then you're gonna end up forming a bromine free radical. So your product here, and you're not generating any chiral center. This is the double bond, and you are making a bromine here with the two alkanes. You are not making any chiral center. See how many products you got. You got 3 products for the second allylic hydrogen, and you got 3 products for the first allylic hydrogen. So you got a total of 6 products. See all of these 6 products in there? You have to write them as products from this reaction. There is no preference of one over the other. All of them, they are going to form, because all of them, they form by breaking the weak sigma bond, which is the allylic hydrogen. Now the reaction goes exactly the same when you are working with a benzylic hydrogen. So if you have a benzene, and next to the benzene, you do have a hydrogen, a benzylic hydrogen, and you are doing MBS in presence of light. So the mechanism is exactly the same. Or if you are doing a bromine in presence of light, both are going to generate a bromine free radical that is going to start the reaction. And here the weakest sigma bond is the benzylic hydrogen on the benzylic carbon. So you are going to replace that benzylic hydrogen with the bromine. You have to terminate your reaction, because if you don't terminate your reaction, the second benzylic hydrogen will also be replaced. So you're going to end up getting a dibromination instead of the monobromination. There are more examples in the problem set. Please work those out.